Hello, my name is Banu Abdikadirova, and this work has been done along with Django Lee, Professor Neville Hogan, and Professor Megan Huber. And in this video, I'll be talking about the entrainment of muscle-reflex model of human locomotion to periodic mechanical perturbations. So locomotion is a crucial component of human mobility, and any type of dysfunction in the gait might greatly impact one's quality of life. In the last decade, there has been dramatic improvement in designing lower limb exoskeletons. However, currently used methods have shown limited efficiency. And one possible reason for that could be that the currently used methods usually impose predefined kinematic trajectories onto the lower limb joints, and that might disrupt the natural dynamics of human walking. It has previously been found that unimpaired human locomotion exhibits features of nonlinear limit cycle oscillators, and one of such features is dynamic entrainment, which means that the period of oscillation synchronizes with an imposed perturbation period with a constant phase relation. And model-based analysis of such important features of human walking is important for aiding our understanding of how behavioral observations arise, and it can also help us to develop more effective methods of robot-aided locomotion rehabilitation. In this work, we determined whether a muscle-reflex model can exhibit entrainment to periodic mechanical perturbations as observed in prior human experiments. And in simulations, we applied periodic torque pulses at the hip and ankle joints, and we quantified a basin of entrainment and phase locking. This slide here demonstrates the results of prior human experiments, and on the left, you can see the phase locking plot of ankle perturbation experiments. And in this set of experiments, they applied torque pulses unilaterally at the right ankle joint in plantar flexion direction. And the experiments have shown that the human entrains periodic torque pulses at the ankle when the pulse period is 50 milliseconds shorter or 50 milliseconds longer than the natural stride period. And we can also see that no matter what the initial pulse phase is, it always converges to 50% of the gait cycle, which corresponds to right leg's terminal stance phase. And on the right side of the slide, you can see the results of hip perturbation experiments. And here, the torque pulses have been applied bilaterally in flexion direction for the right hip and in extension direction for the left hip. And here we can also see that no matter what the initial pulse phase is, it always converges to 78% of the gait cycle, which corresponds to right leg's mid-swing. However, in human experiments, they've only tested pulse periods that are 25 milliseconds shorter than the natural stride period. So for this study, we used an existing muscle-reflex model of Geyer. As you can see from this figure, this model consists of 7 segments, which is a trunk segment and trunk, thigh, and foot segments for each leg. The model also consists of 7 heel-type muscles for each leg, and periodic human-like walking is generated from muscle control signals. So overall, this model can generate stable walking with reasonable accuracy. And what is important to note is that this model doesn't contain any type of supraspinal controller or central pattern generator. This slide here shows our simulation setup. As you can see, for hip perturbation simulations, we've applied hip torque pulses bilaterally. So at the left hip joint, it was applied in extension direction, but for the right hip joint, it was applied in flexion direction. In ankle perturbation simulations, it was applied only unilaterally in plantar flexion direction. So in order to be able to assess if the model has entrained or not, we used 2 criteria. The first one was one-to-one frequency locking, which means that the model stride period should converge with applied perturbation period. And the second one was one-to-one phase locking, which is basically having constant phase relation with pulses. In order to assess the entrainment of the model to ankle perturbations, we did 3 sets of simulations. The first one was focused on determining a basin of entrainment. Here we varied pulse period and torque pulse magnitude by keeping initial pulse phase the same. And the second one was focused on assessing the effect of torque magnitude on entrainment. Here we altered torque pulse magnitude by keeping pulse period and initial pulse phase the same. And thirdly, we evaluated the influence of initial pulse phase on entrainment. The initial pulse phase was changed with a resolution of 100 milliseconds. This slide here shows the basin of entrainment of ankle perturbation simulations, and Each of these rectangles here in this figure corresponds to a single simulation, and the black rectangles represent failed simulations. The color axis shows relative terminal period. So the closer is the value of relative terminal period is to 1, the stronger is the frequency locking. And from our simulations, the model entrained to pulse periods between 78 milliseconds shorter and 7 milliseconds longer than its natural strike period. However, in human experiments, the gate entrained to pulse periods between 50 milliseconds shorter and 50 milliseconds longer. What we can also notice from this plot is that the basin of entrainment is finite and it gets wider with increasing torque pulse magnitude. This plot here shows the effect of torque magnitude on entrainment, and we can notice that the higher is the value of torque magnitude, the more stable is the phase locking. And we can also see that the converged phase relation is independent of torque pulse magnitude. We also evaluated the influence of initial pulse phase on entrainment, and from our simulations, the pulse phase converged to two distinct phases, which was 10.7% corresponding to right leg's loading response and 45.5%, which corresponds to right leg's terminal stance. However, in prior human experiments, the pulse phase consistently locked 50% of the gate cycle, which corresponds to right leg's terminal stance. Heat perturbation simulations was performed in a similar way to ankle perturbation simulations, and here also our analysis consisted of 3 sets of simulations. And the first one was focused on determining the basin of entrainment, where we varied pulse period and torque pulse magnitude by keeping initial pulse phase the same. The second one aimed at assessing the effect of torque magnitude on entrainment. Here we altered torque pulse magnitude between 2 Newton meters and 10 Newton meters. And the third one was focused on evaluating the influence of initial pulse phase on entrainment. The initial pulse phase here also was changed with a resolution of 100 milliseconds. This plot shows the basin of entrainment of heat perturbation simulations, and from our results, the model entrained to pulse periods between 93 milliseconds shorter and 197 milliseconds longer than its natural strike period. So we can see that this basin of entrainment is wider compared to previous ankle perturbation simulations. However, in human experiments, they've only tested entrainment to heat pulses with a period of 25 milliseconds shorter than the natural strike period. Therefore, there is still a need to do more human experiments to see if basin of entrainment is wider. What we can also notice from this plot is that the basin of entrainment is finite and it gets reduced for lower torque pulse magnitudes. The plot here shows the effect of torque magnitude on entrainment, and the converged phase relation is independent of torque pulse magnitude, since no matter what the torque pulse magnitude is, it always converges to the same pulse phase. And the degree of entrainment weakens with lower pulse magnitude. We also evaluated the influence of initial pulse phase on entrainment, and from our model simulations, the pulse phase converges to 94.9% of the gate cycle, which corresponds to right leg terminal swing. However, from prior human experiments, the pulse phase consistently locked to 78% of the gate cycle, which is right leg's mid-swing. To summarize, this muscle-reflex model could competently entrain to periodic torque pulses applied at the ankle and hip joints, as in prior human experiments, and it also showed finite basin of entrainment. In ankle entrainment simulations, the model phase locked to two distinct phases, unlike human experiments. In hip entrainment simulations, converged phase relation was slightly later in the gate cycle for the model compared to human experiments. We also found that torque magnitudes beyond 6 Newton meters didn't substantially widen the basin of entrainment. There are several reasons why this work is significant, and first of all, the model could produce limb cycle behavior without having any type of supraspinal controller or central pattern generator. This means that entrainment is emerging from purely peripheral neuromechanics, and this fact can aid our understanding of how gait entrainment arises. It can also help us determine the potential therapeutic effects of gait entrainment. Thank you for your attention. If you have any further questions or if you want to discuss more about this work, feel free to reach to one of the following people.